Now we turn to the lab exercises. You have seen the ideas on the slides. In these 3 short labs, you write a little C and prove each idea to yourself. This is Lab 1. The goal is simple. You will prove to yourself that addresses are real and that the stack, the heap, and static data live in different parts of memory. First, declare one static int at file scope. Static means it has one fixed home for the whole run of the program. Next, inside main, declare one plain local int and a local array of 4 ints. These both live on the stack because they are locals. Then ask for a heap block. Call malloc for 4 ints and check the result for null before you use it. This block lives on the heap. Now print the address of each one, using %p, and cast each address to void star. Before you run it, make a guess. Will the second array slot sit exactly 4 bytes after the first? Will the stack and the heap land near each other, or far apart? Let us look at one solution. Try your own version first, then compare it with this one, line by line. This is the static int at the top. It sits in static storage, so it keeps one fixed address for the whole run. These 3 lines live inside main. The plain local and the array of 4 ints go on the stack. The malloc call gives us a heap block, and we check it for null right away. These lines print the address of each item. Each one uses %p, and each address is cast to void star. This is the key point. The second array slot prints exactly 4 bytes after the first because the elements sit side by side. The stack address and the heap address fall in different ranges, far apart. Your exact digits change on every run. The relationships do not change. This is Lab 2. There is no new code to write here. Instead, you turn a small heap program into a memory diagram, using pure reasoning about where each thing lives. Read the program first. It sets n to 5, then asks malloc for 5 ints. It checks the block for null. Then a loop fills the 5 slots with 10, 20, 30, 40, and 50. Each slot gets I plus 1 times 10. Now draw the picture. Show the handle on the stack, the heap block it points to, and the address of every element. Pick a made-up base address and step up by the size of 1 int for each slot. Then say this out loud. After you call free on A, what is still true about the value inside A, and why must you never read through it again? Let us check the drawing. Compare your picture with this one piece by piece. This is the memory map. The handle is one small pointer on the stack. It holds the base address of the block. The 5 ints sit together on the heap, and each one is 4 bytes after the last. This box makes the tricky part clear. After you call free on a, the variable still holds the same address. Assignment did not erase it, but the block is gone, given back to the allocator. Reading through a now is undefined behavior. The fix is 1 line. Free-a then set it to null. One run confirms the block worked before we freed it. The array holds 10, 20, 30, 40, 50, and the sum is 150. This is Lab 3. The goal is to see both views of one array at the same time, and to link the logical index to the physical address. First, the code. Declare an array of 5 ints with the values 10, 20, 30, 40, 50. Loop over the indexes 0 to 4. On each line, print 2 things: the logical value at that index and the physical address of that slot using %p cast to void star. Then answer 2 questions in writing. First, by how many bytes does each address grow, and why? Second, which view does the client of an array base type care about, and which view does the person who builds it care about? Let us walk through the solution together and check both answers. This is the loop. For each index from 0 to 4, it prints the value in that slot and then the address of that slot. One line per element, logical value first, physical address second. This is one real run. Read down the addresses. Each address is 4 larger than the one above it. The elements sit right next to each other in memory. Now the two answers. Part A, each address rises by 4, which is the size of one int because the elements are contiguous. Part B. The client only cares about the logical order 10, 20, 30, 40, 50. The person who builds the type cares about the physical layout because that side-by-side storage is what makes reading any element cost big O of 1.